Welcome back to this cute little series in which we implement Conway's Game of Life, which is this simulation, this life simulation right here. And in this episode, we are going to implement the actual simulation logic. Right now, we're at a stage where, let me just show you the Game of Life. Right now, we're at the stage where we have the graphics ready. And we have a matrix, a grid with cells, and the cells simulate. And right now the simulation behavior is just color the cell white and black randomly. So there is no real simulation going on. And in this episode, I would like to implement the actual Game of Life simulation according to the 4 simulation rules for Game of Life, which are any life cell with fewer than 2 live neighbors dies as if by underpopulation, any life cell with 2 or 3 live neighbors lives on to the next generation, any life cell with more than 3 neighbors dies as if by overpopulation, and any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. And right now our data structure, the data structure that is the underlying data that we are animating is the so-called game matrix, which we have initialized here. It's practically just an array of integers, either 0 or 1, depending on whether the cell is alive or not. And the game matrix is initialized randomly at this time. So let me just show you it here. So initialized game matrix is randomly generated here. So the random 1s and 0s are assigned here. And that is fine. We can still initialize the game matrix randomly, but now I would like to compute the actual simulation steps. And to do that, looking at the Game of Life rules, what is apparent that what really counts for a cell, whether it lives or dies, or if a dead cell becomes alive, is just the count of neighbors. So let's just confirm that any live cell with fewer than 2 live neighbors dies. Okay, so we have to count the neighbors. Rule 2, any live cell with 2 or 3 live neighbors lives on. So again, we have to count the neighbors. Rule 3, 3 live neighbors, and rule 4, 3 live neighbors. So the rules depend on the neighbor count, and they depend on whether the cell is currently alive or not. And I guess the first step that we have to do right now, that we have to implement right now, is to implement a method that actually counts the neighbors. And I fear this can be a bit tricky because we're dealing with C, and our data structure is a 2D array of all the cells. Yeah, technically it's completely possible, but it's going to require some thinking. So let me just initialize the game matrix outside of the game loop. That means we initialize it once, and inside the game loop, we can then implement the logic. So let me just also compile the Game of Life. Again, I will call the binary Game of Life, GOL, and use the source code like that. So that compiles, calling Game of Life. We now have the initialized matrix, and it doesn't do anything, of course, because we just removed the initialization from the simulation loop. And inside the simulation loop, we should implement a new method, or call a new method that is not yet implemented, and that is something like process simulation or simulation step. Yeah, that actually sounds quite good. And I will pass the row count and the column count to it, the game matrix, And I think that should be it for now. And the simulation step basically computes the next iteration of the game matrix, which holds all the cell values. And I think that method definition should be complete. So let's just go up here and create a new void method that is simulation step. And the simulation step will be, will take as input, now I have to do a proper definition here, an integer row count, an integer column count, and a game matrix which is an integer array. Okay. Good. And we have to, well, we have to iterate over each cell in the game matrix and count its neighbors. And that is a bit tricky. Let me just see if I still have, no, I don't have our last painting in here, but let me just remodel that. I will use this brush right here, adapt the brush size, and good. Okay, so we want a game matrix which is a 2D grid. Something like that. However, we have a simple 2D array. This means that the first row here must be the initial part here. After that comes the second row right here, etc., etc. And if we're looking at one of the cells, for example, let's have a look at this cell right here, the one I'm coloring in blue, then the neighbors would be the left and the cell left to it, the cell right to it, the cell above it, and the cell below it. I don't think we consider diagonal neighbors. Let me just see if there's a rule here. No, every cell interacts with its 8 neighbors. Okay, we do consider diagonal neighbors. So we have to check left and right on the current row. Then this, which would be those. Then the same coordinates on the above row, if it exists. In this case, it does not even exist. And the same coordinate on the below row. Yeah, that is quite tricky, but definitely doable. We just have to consider the correct bounds. Good. So, where do we start? Starting is always the hardest. I think here in this method we are processing the entire simulation. So we can copy the entire for loop. Let me just delete the printfs here. We can just copy the entire for loop, which iterates over the rows and columns and then accesses the game matrix. Of course, we don't want to assign new values to the game matrix, but this time we would like to count the neighbors for each cell. So how do we properly do that? We'll just drag in this picture here again for visual help. Okay, let's imagine we're at this blue cell. This cell is defined by coordinates I and j, which is the row count and the column count. This means that we have to retrieve the left cell if it exists. So let's just do that. I mean, we have to start somehow, so why not start with just one cell? Let's just get the left neighbor, this one right here. Okay. Maybe we should do an integer neighbor count. And that is equal to count neighbors, count neighbors, and we provide the row count. No, we provide the coordinates at which we are right now. Then the row count, the column count, and the game matrix. And then we perform logic based on neighbor count. And let's just create a new method, count neighbors. Right here, count neighbors. Why am I always writing neighbors? Count neighbors, int I, int j, int row count. I'm passing the row count, by the way, and the column count to make sure when we deal with these border situations, for example here, that we are always able, or no, let's say this one in the bottom right corner, that we are always able to tell, okay, we're at the last row and we're at the last column. Of course, there are probably more sophisticated ways to do that in C, but I like to keep things accessible. Okay, and here we're counting the neighbors. So let's just count one neighbor, which is, let me just fix the row count here. It should be column count. And yeah, so let's just try counting the left-hand neighbor. Left-hand neighbor. The left-hand neighbor would be in the most simple case, the value at game matrix, and then we access the individual cells, like as we did also here in the other methods. So this is our access pattern to access the cell at I and j. Column count. But that does not work, of course. Okay, this should be it. And to access the column to the left, we have to decrement the column count, the left-hand column count, which should be something like that. j minus 1. J is the column indicator. I is the row counter, as you can see here and here. So we decrement j by 1. However, we should only do this, we should only ever do this, and this will only work if we are not dealing with a leftmost cell. So if we were looking at this cell right here, then there would be no left-hand neighbor. So we would have, in this case, we have to check, are we at column 0? Because if we are at column 0, then we can't check the left-hand neighbor. So if column, and that should be if j is equal to we count the left-hand neighbor only if j is bigger than 0. Otherwise, if it's 0, well, we don't count it. Okay. Let's just introduce a new variable in neighbor counter. Neighbor counter that is equal to 0. And I think we can do neighbor counter and increment it by the value of the game matrix at this coordinate right here. So this should be counting the left-hand neighbor. And of course, at the end of this, we have to return the neighbor counter because we promised to count the neighbors in this method. So we actually have to return something. Good. I'm wondering why it shows errors right here. Rows undeclared. Ah, yeah, of course. Rows, columns. Maybe I should change this to rows and columns. Rows, columns. Okay, the left-hand neighbor. Good. Then let's continue with the right-hand neighbor. Right-hand neighbor. If, and we pretty much have to apply the same logic, we can't be at the right border. So if j is smaller than the column count, I think we have to even check column count -1, because the column count, for example, will be 10. No. I think we have to do that because of the array access index, which is always starting at 0, and the column count is of course not starting at 0. Let's see. I will just keep this. If it doesn't work, we can fix it later on. Then neighbor counter is plus equal to incremented by game matrix. Then we will return that. We will increment the column indicator plus column count multiplied by I. Okay. Then next step, the above neighbor. We can only above neighbor. And right now I'm talking about the neighbor that is directly above. This one right here. And of course we can only count this if there's even a row above. So if we have to check that the row counter is bigger than 0. Because if it was 0, there would be no row above. So row counter must be bigger than 0. Then the neighbor counter increments by the neighbor counter increments by this. We have to decrement the row counter by 1. And then we access the value at the same column. Yeah, good. Actually, now I'm noting that in this, no, forget about it. So this is the above neighbor. Next is, let's try this one, the above left neighbor. If I is bigger than 1 and j is bigger than 0, then we can find the above left neighbor. Above left neighbor. And that is equal to j minus 1, and this one is also decremented by 1. This is above left. Now it's getting dangerous because I'm copying a lot. Let's try the above right neighbor. The above right neighbor, for the above right neighbor, it must be checked that I is smaller than the column count minus 1. Again, we will see if that assumption holds. And j must be, j must be the column count minus 1. J must be smaller than column count minus 1, and I must be, well, we must have an above neighbor, so I must be bigger than 0, so that is still valid. So here we are looking at the right neighbor. So that's why we're doing plus 1. And then the column count multiplied by I minus 1. Yeah, that looks good still. So we should have all above neighbors now. Here we're just checking that I is bigger than 0. And we're getting the one above. Then we're getting the one to the left, one to the right above. Yeah. So let's copy all the above stuff and adapt it for below. Below. Okay, for below. Let's open the graphic again. Let's imagine we're accessing this cell right here, the orange one. In this case, the below neighbors would be, well, no, it would not have any below neighbors, so bad example. But yeah, we would have to check that the row count here is not exhausted. And of course, the column count can't be as well. So let's check. I must be smaller than the row count. I think -1, because we're accessing by index. Yeah, because if I is smaller than row count, then it would be row count -1, and then I'm not sure. I think this is the right thing to do here. I just feel it. But we can remove the -1 if it's not necessary. Then the neighbor counter is incremented by the game matrix value at J, the same column, so that is good. And the row, the row below. So we increment the row value. Yeah. Let's do the same here as well. We just have to check the left neighbors. So we do AJ -1. And we of course have to adapt the conditions. So I is smaller than row count -1. And J is bigger than 0. Yeah, that looks good. And the below right neighbor. Oh, excuse me. The below right neighbor will be smaller than row count -1 again, just to check that we're not exhausting the rows. And the column count needs to be smaller than the column count -1. I think that is good. And the neighbor counter is incremented by the column to the right and the row to the bottom. Good, let's compile that. Probably it's not doing anything yet. Yeah, of course, because we haven't started, we haven't implemented this in the game loop. So right now we're counting neighbors. I hope there's no bug in there. Dear God. No, I'm just joking. Do not misuse prayer for such stupidity. Simulation step. I++, J++, int neighbor count. So the neighbors are counted here. Right, and now we have to perform logic based on the neighbor count. And based on the neighbor count, we do follow the following rules. We have to get the current cell value. Is the current cell alive? Int current cell value. Or just current cell value. The current cell value is the game matrix at J plus column count or columns multiplied by I. Just following the same pattern as always. And so that is the current cell value. Good. And then we would have to, well, if the current cell is alive, let's just try to do rule 1. Any cell with fewer than 2 live neighbors dies, as if by underpopulation. Okay, so if the neighbor count of the current cell is smaller than 2, was it smaller? Fewer than 2. Does that include or... No, that does not include 2. Okay, if the neighbor count is smaller than 2, then we don't actually even need the current cell value. In this case, we will just let the cell die. So we are going to set the game matrix at these coordinates to 0. Then any live cell with 2 or 3 live neighbors lives on to the next generation. Okay, so if the current cell value is not equal to 0, so that means if the current cell is alive, I'm just considering that there may be a value that is not 1, it might be another value, not 0. Of course, we're just dealing with 1s and 0s, but this is a bit more robust implementation. So if the current cell value is not equal to 0, which means the cell is alive, then we have to, what was the rule again? My short-term memory is not great today. Any live cell with 2 or 3 live neighbors lives on to the next generation. Okay, so the cell is alive. Okay, the cell is alive and the neighbor count is either 2 or 3. Neighbor count is equal to 3. In that case, we can just continue the loop. Because in that case, the cell lives on, the cell is already alive, and the cell lives on. That means we don't have to do anything. Any live cell with more than 3 live neighbors dies, as if by overpopulation. So here, we have to change the cell state again. Any cell with more than 3 live neighbors dies, as if by overpopulation. Okay, that applies to alive cells. If current cell value is not 0, that means the cell is alive, and neighbor count bigger than 3, or was it 4? Yes. Then we set the game matrix at this coordinate to 0, so the cell dies. So far we have only let cells die and we have let cells live, but we haven't reproduce any cells, which is rule 4. Maybe I should write comments here. So that is rule 1. This right here is rule 2. And this one right here is rule 3. Any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. Any dead cell, that means rule 4. Dead cell means the current cell value is 0, and the neighbor count, I think it was 3 or more, is over 3. Actually, it's a lot. Maybe 2. With exactly 3 live neighbors. Okay, interesting. Then the game matrix at this coordinate will be 1. And that should be it. I'm just wondering where the error is. Right now my language server is telling me expected expression before this brace. What expected expression? There seems to be an issue with the continue. Expected bracket before continue. Wow. Okay. Yeah. Yeah. Of course. There was a bracket missing there. Okay. That compiles, and if we execute the game of life, ooh, I think it's working. Is it working? It looks a bit too cluttered for a game of life, actually. But it's definitely not working. No, actually it looks good. I mean, we have initialized the entire grid with a lot of alive cells. So that might be the reason. Maybe this is already bug-free, but that would be very surprising. It's extremely rare that I implement anything bug-free on the first try. So let me decrease the delay here, and in the initialization of the game matrix, which we might adapt later on as well, I will make the alive cells a bit more rare. So the random number must be let's just I'm not sure if that is even a good solution. How do I get a rate of 30%, for example? Nah. So here the values a random integer in the random function, and the modulo 2 ensures that it's either a 0 or 1. But I would like to have more zeros. Can I just do that? Let's see. This should be 25% now. Yeah. Oh, I think it's the game of life. It really behaves like it. That's awesome. That's so awesome. Oh my god. Okay, what can we do now? Let me just make it a bit more rare. Oh yes, that's definitely game of life. Oh, this is so awesome. Great. And maybe we can tweak it even and make the the grid a bit more, a bit tighter, the cell width. Can we adapt the cell width and just say that a cell should be 20 pixels instead of 30, so we get a bit more graphics going on? I think, why is it spreading so much? Is Game of Life really spreading that much? I'm not sure. We have to confirm the rules. We have to check the neighbor counts maybe. This looks too alive. Let me just decrease the cell width again. So let's see what happens with even more cells. No. I have to recompile, of course. Yeah, somehow it spreads too much. But it looks really cool, I mean, especially in the beginning. But life does not spread so much. I mean, some things should die here, especially due to overpopulation. So either the neighbor counting is broken or something else. Yeah, so we have to adapt that. So let's see. Count neighbors, the neighbor counter. If j is bigger than 0, neighbor counter. Okay, this is the left-hand neighbor. A left-hand neighbor only exists if j is bigger than 0. That is fine. Then the neighbor counter is incremented by the game matrix value at j minus 1. Good. The right-hand neighbor. For the right-hand neighbor, we access j plus 1. For the above neighbor, we access j and I minus 1. Good. For the above left neighbor, we have to check that I and j are both bigger than 0. And j is j is decremented, I is decremented. Actually, that looks good. Above right neighbor, so we still have to check above whether an above exists. And j must be smaller than the column count. Yeah. Looks good. I don't see why it wouldn't work. Then the below neighbor is for the below neighbor, we're at this line right here. We have to check that the row count is not exhausted, and then we are accessing the same column j at the next row, so that looks good. Then row count minus 1, j is bigger than 0. For the below left, and the below right is row count minus 1, yeah. Okay, I think it's good. Let me just insert a printf neighbor count just to see and confirm that the neighbor count produces valid looking values. So let's switch over into this pane here, compile. Oh, yeah, of course I have to provide the neighbor counter here. So let's switch over to this compilation pane, compile. Let's see. Aha, okay, so it looks reasonable, but yeah, I think the values, they switch a lot between 0 and 4. Does that make sense? Sometimes there should be more neighbors, no? No, actually, it looks reasonable. Let's have a look at a different place in the code. Maybe the rules are not correctly implemented. So the current cell value is retrieved here. Rule 1 was any live cell with fewer than 2 live neighbors dies. So this is dying of cells. This is actually why, if dying was wrong, then we would have overpopulation. So this is something we have to be careful with, especially because we see a huge population. Any live cell with fewer than 2 live neighbors dies, as if by underpopulation. The neighbor count is 2. So we set the value of the matrix at that coordinate to 0. Yeah, the neighbor count is smaller than 2, fewer than 2 live neighbors. So that seems to be fine. Rule 2. Any live cell, so current cell value must be unequal 0, with 2 or 3 live neighbors lives on to the next generation. Yeah, okay. Rule 3. Any live cell with more than 3 live neighbors dies, as if by overpopulation. Again, dying important. Any live cell with more than 3 live neighbors dies. Cell is live, cell is alive, and the neighbor count is bigger than 3. Looks okay, actually. And any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. Any dead cell with exactly 3 live neighbors becomes a live cell. So actually, I think the code is okay. I don't like the continue statement here, so let's just explicitly set it to 1, although it's not necessary for rule 2. So if the cell is alive, then it's going to stay alive. If the neighbor count is smaller than 1, the cell is going to die. And when else is the cell going to die? Ah, okay, that looks actually quite good. I just made the initialization matrix a bit more strict in that sense that ones or live cells at the initialization are more rare. So, why does it start the same thing over and over? Huh? By the way, Is this game of life? I might need your help on this. Please write in the comments whether that is a valid game of life. It might be. It looks really alive. And it looks stable. In a sense that not everything becomes white and not everything becomes black. So the cells really appear to be living and dying. I think this is a valid game of life. Let's make the simulation even faster. How fast can we get it? Interesting. Let's check how to make C generate 0 or 1 with probability. Maybe we can just check for rand is bigger than, and the random function, crand function. Let me show you what I mean. The random function returns a value between 0 and I think some maximum value, depending on the compiler or depending on the processor. I don't remember. Up to rand max. So if rand is bigger than rand max divided by maybe we can do 2/3 like that. So 2/3 of the values are going to be 0. Yeah, looks okay. What if we made 9 out of 10 of the values 0? Does that work? Yeah, okay. I'm just not sure about why this is spreading so much. That is the only thing that is bugging me. Because if we are starting a game of life here, let's just have a look at how it behaves in the browser. Can I just draw something? Let me just do that. usually things don't just grow arbitrarily. You see? Oh, it's a bit different. So you have a couple of rockets going off, a bit of flickering here and there, but there's no this. So we definitely have to fix something here. So what is the issue? There needs to be some issue. Let me have a look at a different source regarding the Conway's Game of Life rules. Conway's Game of Life rules. Maybe the Wikipedia rules are not valid. A life cell dies if it has fewer than 2 live neighbors. Rule number 1. Live cell dies if it has fewer than 2 neighbors. Live cell with 2 or 3 neighbors lives on to the next generation. Maybe just let's make it more explicit here. Rule number 1 is a live cell dies, so the current cell, although this is not really necessary, but the current cell value must be 1. Must be unequal 0. Still the same behavior. Okay. A live cell with 2 or 3 live neighbors lives on to the next generation. A live cell with 2 or 3 neighbors lives on to the next generation. Good. A live cell with more than 3 live neighbors dies. A live cell with more than 3 live neighbors dies. A dead cell will be brought back to life if it has exactly 3 live neighbors. A dead cell will be brought back to life if it has exactly 3 live neighbors. So I think the rules are fine. Why is this spreading so much? Something is not fine. Let me just tweak the rule number 3 and see what happens if we change this neighbor count to 2. Okay. Yeah, they die pretty fast. Maybe we do have to use else if. Maybe multiple rules can apply at the same time. I'm not sure. Let's just make sure that our if else is rock solid. So let me just do the braces here. And then rule 2 will be else if. This shouldn't be necessary, but I just want to make sure. Then else if Now come on, where have I gotten? Else if brace and brace. Okay, this behavior is still the same. That means the rules were probably okay. Or they are still unchanged. What about this case? Maybe this is just the time and place where we should just check how the system behaves if we remove the column count -1 and the row count -1. The thing I talked about earlier. But I think this will break now. No. It doesn't break, it still behaves weirdly. Is something wrong with the counting? Neighbor counter is incremented by that. Let's do an extreme case and check if the neighbor counter really works. We can do that by just misusing some of the code here. I will initialize a fake game array, which is going to be this matrix right here, or a similar matrix, just a short one with 3 rows, 3 columns. And let's see if it works. So the values are going to be 1, 1, 1, 1, 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is our fake game. So here, if we count the neighbors, at the middle of the game, so we provide 2, 2. So let me draw for you what I'm thinking. I'm thinking of a game like this, and all the cells are alive, and I'm checking the neighbor count for this cell right here. So the neighbor count should be 1, 2, 3, 4, 5, 6, 7, 8. And the coordinates of the cell we're checking is 1, 2, 1, 2. No, it's 0, 1. 0, 1. It's 1, 1. Because this is 0, 1, 2. Aha. 0, 1. The length, the row count is 3. The column count is 3. And the fake game is this. And then we do the fake count. Well, we should actually call this test count, but yeah. Test count is equal to let's see what the printout says. It's 5, so the counting is not properly done. It should be 1, 2, 3, 4, 5, 6, 7, 8. But I think we have to do the -1 here again. Let me just copy this into... How do I do that? Yank. Okay, let me just undo those -1 index changes here and paste the counter again. Yeah, so let's try to seed using the current time. I would like to come on, where have I been? srand time null. I need to include time.h, time.h, and then I will call srand time null. Interesting. Okay, there seems to be an error in the last line. What is it? Expected identifier, so there's a missing brace somewhere, and it is here. Oops. At least we're starting with a different population this time. Okay, this seems to be... Okay, so at least we can now see that sometimes populations are stable and sometimes they aren't. Or they are stable when they don't reproduce, and they aren't stable if they just arbitrarily grow exponentially. This looks quite interesting. So this is now a stable population, as in it does not even evolve. I am not seeing the typical Game of Life rockets. So let me just confirm something. J, I. That's good. IJ, rows, columns, game matrix. Rows, columns, game matrix. I0, I smaller than rows, I++. J0, J, columns, J++. Okay. Current cell value is this. I will just copy this, and this time let me ask ChatGPT this time, because I'm actually quite sure that the rules are okay this time, but I'm wasting so much time. Okay. That is it. I would not have figured that out. So I have asked, are the rules of Game of Life correct in my C implementation? And I pasted that code, and then ChatGPT responds with the rules for Conway's Game of Life C to be implemented, but the logic might not work as expected. And the reason is we are modifying the individual cells of the matrix on the fly. And in the next iteration, for each cell, the previous cell has already been modified. But instead, we have to create a temporary matrix in which we store all the cell values and then copy them over. So this is what we need to do. We need to create a new matrix. You know, because we have to code the simulation step on the entire matrix. I mean, the next values are based on the current matrix. But in this loop, we are modifying the current state of the current matrix for each cell in each iteration. So we're changing the state of the matrix inside the simulation step. But inside the simulation step, we should not change the values here. So this is something that would have taken me so long to figure out. So I'm glad I just asked GPT in this case. And I think just in general, this is a good application of ChatGPT just to find such things. Don't use it to generate code for you. because then you will learn nothing. But this is a good application to just save you time for something that you would not have figured out otherwise. So now let's just do that. So int next game matrix, and that is a new array of size rows multiplied by columns. And then the next game matrix always receives those values. Oh. Next game matrix, next game matrix. Return next game matrix. Okay, so here we're actually returning something now, so we need to change the method signature. I hope this works. And here we're performing the simulation step. Int next game matrix is equal to that. Or no, maybe we should not return things, because in that case we would have to store temporary variables, and I don't really like that. So let's do next. Let's keep this a void return value. Then we write into the next game matrix, and in the end, for every int I equal to 0, I smaller than rows multiplied by columns. So we copy the matrix over, and we write game matrix at I is equal to next game matrix at I. So we're copying the next game matrix over. Maybe we should rename the next game. Oh no, let's just keep it like that. And let's compile and see how Game of Life behaves. Ooh, what the hell is that? What the hell is the bottom part here? Oof. That looks ugly. And the bottom part is misbehaving all the time. So something is not correct. ChatGPT was also adding a case. Yeah, sorry for the unexciting ChatGPT part now. It was adding a case here where the next game matrix where this is being done. Just in case none of the rules apply, but I don't think this I'm not sure if ever none of the rules applies. Because let's just compile it. Oh, this is working now. So it does seem to be the case that if none of the rules apply, what is the case where none of the rules apply? No, I think maybe we have to make sure that every value in the next game matrix is set. Otherwise, it will contain random values and we will get weird, unexpected behavior. But this is now definitely working game of life. This is the way I would expect it to look like. Okay, the moment I say working game of life, it stops working. Why? Oops. This is good. This is the way I know game of life. This is also good. Yeah, and there's a rocket. This is a perfect sign of a working game of life. This is awesome. Okay, so we coded game of life ourselves, but in the last detail we wasted so much time on was calculating the next simulation step, and we made the mistake, or I made the mistake, to modify the game matrix while the simulation was ongoing. And that was the big mistake. And we actually need to create a temporary matrix and write the values over once the entire matrix is processed. So that is the small detail. I'm not sure how much time this would have taken me to figure out on my own. So I think it's a good thing to ask an AI in that case. So I think we can change the game matrix initialization to be random again, random modulo 2, because now we have a working game of life and we can just check what's going on here. Yeah. And you know what? Now that we have a working simulation of the game of life, we can actually make this a bit more interactive. How about during the loop, or even before the loop, we can set our own cells that we want to simulate by mouse clicks. So that is something we will have a look at in the next episode. And if you enjoyed this episode, then please leave a like and let's see you next time. I'm very happy with this game of life and actually surprised that we have a working implementation already in the 3rd episode. And yeah, this is quite cool. So if you enjoyed watching this, then see you next time. Bye.